Welcome back to Electronics, Simple Circuits and Measurements Fundamentals. In the previous module, we used our resistors to build a voltage divider with our 9-volt battery. In this module, we'll introduce more circuit components and explore new modes on our multimeter that will allow us to measure new circuit characteristics. Recall back to our previous module, where we constructed a voltage divider and measured voltages between the resistors. How did we combine those resistors? We linked the resistors one after another, in series. Detaching ourselves from the goal of reducing voltage for a moment, let's consider a different way of connecting two resistors together. Rather than one after another, what if we placed them next to each other? This configuration is called a parallel circuit, because the resistors are alongside one another. Notice the fork or split in the current path in this circuit. When current comes from the battery, we reach the fork in the road. Some of the current goes down one path, the rest follows the other path. The amount of current each path gets depends on how much resistance each path has. If what we made before was called a voltage divider, what would you call this one? How about a current divider? We won't cover this until our next electronics workshop, since current loop calculations are a bit tricky. But it's interesting to note that in this configuration, the voltage drop across both resistors is the same, 9 volts. Even though there are two resistors and they're different sizes, the voltage drop is the same across them, since they are in parallel. This is antithetical to the voltage divider, where we have the opposite case. The voltage across each resistor drops according to the size of the resistor, but the current through both those resistors is the same. But I digress. Back to the voltage divider that we made in the previous module. Let's take a closer look into how we made our measurements. Sure, we connected the resistors in series, but how did we integrate our multimeter to make those voltage measurements? We measured across the resistors, placing our probes on either end of the resistor. This means that we hooked our multimeter up in parallel, since the multimeter is running parallel with the resistor itself. In this configuration, you can see that while electricity flows through the resistor, it also splits off and flows through the multimeter. To reiterate, to measure voltage, you measure across in parallel. So we integrated our multimeter in parallel to measure voltage in our voltage divider. But how would you connect it in series? And what could you measure if you did? Well, a series connection means that one element leads into another. So the first step will be to cut into our circuit and splice in our multimeter probes. Now, electricity flows from the battery through the first resistor, through the multimeter, and then through the second resistor back to the battery. Great! We've placed our multimeter in series with the circuit. But what can we measure now? As it turns out, this is how we measure current. Let's rotate our multimeter dial to A, representing amps, which is short for amperes, the unit of measure for electrical current. When we do, we measure the amount of current that is flowing through the circuit. Interestingly, if we do this before the first resistor, rather than between the two, we'll get the same current measurement, same as if we splice in after the second resistor. The current through the circuit loop is the same throughout, and is only split if the circuit forks, but we'll save that for another workshop. Let's introduce a new player in our lineup of electrical components, the Light Emitting Diode, or LED. While it's something that you've likely encountered today already, let's break down the name to understand its function. First, light emitting. Pretty straightforward. This element produces light. Very cool. When we attach a battery, the LED lights up. But what about the word diode? It turns out that diode is like a one-way valve. It allows current to flow in one direction, but not the other. So, if we connect this thing backwards, it's not like we'll get negative light. We just won't get anything. You can use the diode check mode on your multimeter, designated by this symbol, to determine in which direction the LED should be connected. But be sure to notice that the wire legs of the LED are different lengths, and the plastic housing of the bulb is asymmetric, suggesting that it should be connected in a certain way. Take a moment to pause the video and use the diode test function to figure out which direction your LED should face. Take note of some of the physical characteristics of the LED, which will help you remember which direction it will face next time you use one. Now, admittedly, I've left out an important detail. While applying voltage to an LED in the correct direction will allow current to flow and the LED to glow, an LED is only able to consume a small amount of energy. An LED is typically rated for about 2 volts and will consume 20 milliamps. If given more than that, the LED will melt and break. So how do we fix this? How do we restrict and effectively reduce the amount of current that our 9-volt battery would push through our LED? Pause the video to think about it. We need a resistor. Integrating a resistor in series with the LED will reduce the voltage applied by the battery, effectively limiting the amount of current that is forced through the LED. This LED protecting resistor is affectionately called a current limiting resistor. In our next module, we will use current limiting resistors to safely illuminate our LED using our 9-volt battery, and use our new measurement techniques to verify that we are effectively throttling the current as we intend.